This is page 21 in your packet. We're going to continue using the second derivative today, but instead of using the second derivative for maximums and minimums, we're going to use the second derivative to find inflection points. So let's start with some prior knowledge. If both the first derivative at p equals 0 and the second derivative at p equals 0, then that means the second derivative test does not tell us anything. However, the first derivative can still be useful, where we would make a chart and find out if we're increasing and decreasing, just like we did in the beginning. So recall that if the first derivative changes from positive to negative, what that would look like, positive is increasing, negative is decreasing, there's a maximum, a local maximum. But if it changes from negative, which is decreasing, to positive, increasing, there's a local minimum. So here's our new concept for the day. A point at which the graph of a function changes concavity is called an inflection point. So we're going to draw two pictures. We have concave up, changing to concave down. Right here, and we're going to have that be an x value of p, is the inflection point. Here the concavity is up, meaning the second derivative is positive. And over here it's concave down, meaning the second derivative is negative. And right here in the middle is the inflection point. We can go the other way. If we start concave down and then change to concave up, again, here's our inflection point. On this side, the second derivative is negative because we're concave down. And over here, the second derivative is positive because it's concave up. So, where the second derivative at p equals 0 is an inflection point, and when the second derivative is greater than 0 on any interval, that's concave up. Remember, up like a cup. And when the second derivative is negative, that's concave down. Okay, so let's put this knowledge to use. Find the inflection points of this function and sketch a graph. Okay, so for inflection points, we're going to need the second derivative. So first, we have to find the first derivative. Use our power rules. Then the second derivative, 6x minus 18. Okay, so when the second derivative equals 0, we will most likely have an inflection point. So let's solve this. X equals 3. Now to ensure that at 3 is actually an inflection point, we have to check to see if the second derivative is going to be changing from positive to negative on either side. So what we're going to do is make a chart where at 3 we know that this is x, and this is going to be the second derivative. At 3, we know it's 0. So here we want everything less than 3, and over here we want everything more than 3. So pick a number, any number less than 3. Let's choose a nice one of 0. If we plug 0 into the second derivative, or here, if we do f double prime of 0, that's going to be 6 times 0 minus 18. That's a negative number. Negative. Now let's pick a number more than 3. So let's pick 4. When we plug that into the second derivative, 6 times 4 minus 18, that's going to be positive. So we change from concave down to concave up. So x equals 3 is the x coordinate of the inflection point. So when it says find the inflection point, we found the x coordinate, 3. Now we need the y coordinate of the point, and we're going to use the original function. We're going to do f of 3, back up here with the original. So take out your calculator so we can calculate that. With your calculator, when you plug 3 back into the original function, a very large negative number, you should get negative 146. So this is the coordinate of the inflection point. And for sketching the graph, you can look at that in your calculator, y equals. You'll know that you have to zoom out very far because of this y value of the inflection point. We're going to skip over number 2. Let's look down here at the note. The reason we have to check, like we just did for this problem, whether you go from concave down to concave up, meaning you change concavity, it's an inflection point, is because not every point where the second derivative equals 0, or when the second derivative is undefined, is an inflection point. Just the same as that not every point where the first derivative equals 0 is just as not every point where the first derivative is a local max or min. Because for this, you also have to change signs from increasing to decreasing or decreasing to increasing. Find the inflection points of f of x equals x to the fourth. Okay, so look, now we actually have a chart here. So you draw this chart in your packet. Find the inflection point, we need the second derivative. So let's find the first derivative. The second derivative. So where the second derivative equals 0, will hopefully be an inflection point. Let's see. 12, x squared equals 0, square root both sides, x equals 0. We actually need another box here, sorry about that. So x equals 0. The second derivative is 0. So maybe it's an inflection point. So here we have to look less than 0. Here we have to look more than 0. So when we plug a negative number, let's pick negative 10, into the second derivative, we get 12 times negative 10 squared. Well, that's going to be a positive, since the sign is positive. We pick a number more than 0, let's do positive 10. We plug that into the second derivative. It's also positive. So there's no change in concavity. That means this is not an inflection point. This is concave up. This is still concave up. So let's look at what the graph of x to the 4 looks like in your calculator. So in y equals, I'm going to put x to the 4th. Graph it on the normal window. Sure enough, there's no change in concavity here, which means there's no inflection point. Okay, so a function f has an inflection point at p if the first derivative has a local maximum or minimum at p, meaning the sign changes, or the second derivative, if the second derivative changes signs from positive to negative or other way around, negative to positive at p, which is why we would make this chart. Okay, so we're draw the first derivative, draw f times w. Okay, I'm going to modify these instructions here a little. So here's our original f of x graph. Where are the inflection points? Let's sketch them on the graph. It would be here. This is concave up, changing to concave down. Oop, changing to concave up, so approximately here. Then we change concavity again, right about, let's say here. So there's 3 inflection points on f of x. So now if we're given a derivative graph, a first derivative graph, the inflection points happen where the first derivative has a local maximum or minimum. So the inflection points on the original g of x So the original g of x has inflection points when the first derivative has a minimum, a maximum, a minimum, and a maximum. Or, now if we have the second derivative here for h prime, it's when the second derivative changes signs. So the original h of x is going to have inflection points. Well, this is positive, positive, positive. Oh, here it changes from positive to negative. And then we're negative changing to positive here. So there's 2, oh no, wait, one more. Positive values to negative values. So here's the 3 places, the 3 different x values where h of x will have inflection points. Okay, so for the remainder of class, you're going to work on your homework. You can skip number 7 and 8, 6 and 7. So you're going to do 1, 2, 3, 5, 8, and 13. But for 5 and 8, only find the inflection points. You don't have to follow the directions that are printed. Make sure this evening you check all your answers on the posted flip chart on Edline.